Hello everyone. We present EDMP, an ensemble of cost-guided diffusion models for collision-free motion planning. Over the years, many approaches have tackled the task of motion planning in robotic manipulation, including classical planners and deep learning-based approaches. While deep learning-based approaches significantly improve the success rate, classical planners are easy to adopt on any new scene without requiring specialized datasets. We propose EDMP to bridge the gap between classical and deep learning-based methods, thereby improving the success rate of classical planning, performing at par with deep learning-based methods, while exhibiting remarkable generalization capability. We first train a diffusion network over a large dataset of trajectories to learn a prior over kinematically valid trajectories. We do not impose any scene-specific context, such as collisions, at this stage, and the network only learns to generate diverse kinematically feasible trajectories. Scene-specific costs, such as the collision cost, are incorporated directly at the time of inference. In this setting, we compute collision costs for each of the intermediate trajectories predicted by the diffusion network at each intermediate step and modify the trajectory based on the gradients of the collision cost. As can be seen, this allows the network to modify the trajectories using the guidance directly for the given scene at the time of inference. However, as shown here, like classical planners, relying on a single cost function or a fixed set of hyperparameters for our guide may prove inadequate in accommodating the nuances that vary with different scene settings and arrangements. Therefore, we propose ensemble-of-costs guidance in which we use multiple cost functions to guide the diffusion. This approach allows us to concurrently account for all possible intricacies across the scenes, significantly enhancing the overall success rate, without increasing computational time. In this slide, we can see 12 guides working in parallel, where the enlarged green boxes indicate collision-free trajectories and the red boxes indicate failed trajectories. During inference, we select the best among these 12. We show some examples of the scenes that are successfully solved using EDMP. Our framework can seamlessly adapt to new settings, including manipulation with different objects in hand, without the need for any retraining. Here, we can see how the guide influenced the diffusion's trajectory differently when holding an object compared to when not holding one. Behavior cloning approaches like MPyNet struggles to adapt quickly to such new unseen scenarios and necessitate retraining. We can see MPyNet's failing here, while our framework succeeds. Lastly, we demonstrate multimodality, allowing users to select their preferred trajectory from the generated set. We believe this capability to produce diverse multimodal trajectories holds significant potential for future downstream applications.